In this video, we'll continue our discussion of section 7.4. This is the convolution theorem. So this is making the process of the last video simpler for us. So what this says is if I want to take the Laplace of a convolution, then I could just multiply each function's Laplace transforms. Now, there are a couple things. It does have to be piecewise continuous on this interval and of exponential order. Piecewise continuous means that every piece needs to fit each piece. And then exponential order is there's some m. That way we take the function times this e and it'll stay under it. We'll leave that be if you need to look those up. For most of the cases in this section for this class, they will be that so we can practice our convolution theorem. So we're going to prove it real quick. This proof is a bit much. So go slow with me. Okay, so starting off with our proof, we're going to let the Laplace of f of t equal capital F of s, which is going to be the integral from 0 to infinity e to the negative st times f of t dt. Or let's go to tau here, actually. Forgive me. Times f of tau d tau. There's a reason, because we're going to call the next one a different variable. Right, and we're going to let the Laplace of g of t equal capital G of s, and that equals 0 to infinity of e to the negative s beta times g of beta d beta. So I guess there's an and here. Okay, we'll let those be that definition. So we're going to work backwards. We're going to start from here and try to get it to there, proving equality. All right, so that we'll start with f of s times g of s. That's just the integral definitions times each other. So we'll do negative 0 infinity, 0 to infinity, and then we'll put e to the negative s tau, and then e to the negative s beta times f of tau times g of beta times, and then we could do any order we want really here. So what we'll do is we'll do d tau d beta. All right, so I think our first step is pretty obvious here. If you can't see it, that's okay if you can't. I've done a lot of proofs. So I'm going to take, not that, going to duplicate this, and we're going to just put our e's together. That's what I was talking about that. We do it a lot. My iPad's being funny today. This is just going to be a negative s, and it's going to be tau plus beta. Right, because I can just add them together and then I factored out a negative s. All right, so it would make sense then to do some t substitution, little t, and we're going to say let that be tau plus beta. Right, if I have that then dt, and I'm going towards, I could pick either one here, but I'm going to pick d beta for this. So we're going to use that first, and we'll let the tau go on the outside. I can flip them because they're piecewise continuous and of exponential order. Okay, so I can go from that, and then let's go ahead and do our replacements. I'm going to go ahead and split some stuff up to make it maybe a little easier on us. We'll go 0 to infinity, f of tau, we'll let that be on the outside, and then 0 to infinity, well, let's put this in brackets, maybe that'll help. E to the negative s tau plus beta, and then f of tau, f of tau got moved out, and then g of beta. D beta, and then d tau on the outside. We flipped them. All right. If I do that sub, now we'll do the sub. I think it'll make more sense here. All right, so we get the integral of 0 to infinity of f of tau. And then these were betas. So if 0 is beta, then So because we're going to little t, t will be tau. So beta was 0, and we're going to little t. So I'd put beta right there, right there, and tau plus 0 is tau. Infinity stays the same, nothing happened there. And then I have negative st, and then g of, and then beta is going to become t minus tau dt d tau. All right, so that was all of our subs there. I can move things in. So I can do 0 to infinity, tau to infinity, e to the negative st, f of tau, g of t minus tau, dt d tau. All right, we're actually almost there. You can see that the e to the negative st, I can actually flip my bounds. So that's going to be the first thing that we're going to do to make our life a little easier. And to see this flip, we're going to have to take a look at a picture. Right now, we have two different axes that we're integrating against. We have the little t axis here, and we have the tau axis. Right now, our bounds say go from tau. So we have this t equals tau here, right in the middle. And we're integrating from, and this is matching our t, starts at tau and goes forward like that. And then that's what keeps us in the tau. It just says go from 0 to infinity, but this arrow, this tau, is keeping us in this triangle to get this area. Okay, so that's the area that we're integrating against. So if I just want to flip my bounds, this is where in Calc 3 a lot of people miss points. We'll still have 0 to infinity for dt, but what's going to happen now is it's not just going to become little t to infinity. We got to go from here to here, and then 0 to infinity for little t, which is what gets us left to right. But this now goes from 0 to little t. Nothing else changes inside of here. And then d tau. We have to make sure that we're integrating over that same area. Okay? So now we have that set up, right? The first integral is with tau. So I can go ahead and put 0 to infinity, and then I'm going to bring out this e to the negative st. And then I'll have 0 to t of f of tau, g of t minus tau, d tau, dt. But if you take a look, this thing right here is the definition. That's not a 6. It almost looks like my 6. This is a t. That is the definition of convolution. So this is 0 to infinity of e times negative st and the convolution of f times g. All right, well, if you look, that is actually just the Laplace of s convoluted with g. Oof, that's an exhausting proof. It's a lot of moving parts that I would have had a hard time, like the whole moving the bounds around. I don't know if I naturally, like me looking at this, I don't know if I would have naturally came up with that. Usually what we can do is we can work our way backwards maybe and try to figure it out. I won't ask you to prove this for me, but it does use a lot of Calc 3 ideas. So if you haven't had Calc 3, the whole switching of the bounds and how you have to change the axes might feel pretty foreign to you. But that's what's coming in Calc 3. I will keep things, you don't have to prove this. So, all right, so let's go ahead and put it into application with 3 problems here, and show you how it makes our life easier. So let's start with A. Okay, A says take the Laplace of the 0 to t of cosine of tau d tau. All right. Well, this is just the convolution. and this might seem kind of weird, but this is the convolution of 1 convoluted with cosine of t. Should you think about it for a moment? If this is f and this is g, so f of t is 1, so f of t minus tau is 1. It doesn't change. And then the g of function, right, g of t is cosine of t. Or you could think about it the other way around, if that's bothering you because it doesn't fit our definition exactly. You could call these g's, and then, f of tau there would be the cosine of tau. All right, so that's where those come from. This definition says, and I'm going to get rid of, actually, I'm going to move this. We're fine. So this is the Laplace of 1. This is what the theorem says. Laplace of 1 times the Laplace of cosine of t. And that's 1 over s times s over s squared plus 1. And that's just 1 over s squared plus 1. Okay, and then if we were doing an inverse Laplace, that would become a sine t. Okay, so I'm going to shrink some things up for room's sake for me. So I'm going to put this right here. Okay, put B, and I think I'm going to split this because I'll have room for it. So B, I'm going to go down for this one. Okay, Laplace of the integral from 0 to t of tau sine tau d tau. All right, this one's kind of tricky. It's kind of interesting that somebody came up with it this way. This is the same thing as the Laplace of 1 convoluted, or let's flip them to make more sense out of it. T sine t convoluted with 1. It's that same trick that we used above, so that we have that 1, but we're going to let that whole t sine t be 1, because if this is the case, then this is just the Laplace of t sine t, which we have a theorem now, times the Laplace of 1. This t sine t, if you don't remember, is -1 to, it's the power of t that decides everything, times the first derivative, because it's the first power, of the Laplace of sine of t. And then I'm going to go ahead and put 1 over s for that Laplace of 1. Right? I'm going to get a -1 over s out front. And then it's going to be the derivative of, and then its sine of t is going to be 1 over s squared plus 1. And then that 1 over s I put out front, if you're wondering where that went. This is -1 over s times the derivative of s squared plus 1 to the -1. I know a lot of you, we need to think about it that way. I'm going to get a -1 over s times a -1. I'll go ahead and write it out. Times s squared plus 1 to the -2 times 2s. All right, couple things. The negatives cancel, the s's cancel. I'm just going to have a 2 on top and an s squared plus 1 squared on the bottom. So there is our answer there. All right, so if you know the theorems, which you'll have the theorems, right, you can just straight up use them with the definitions. Just got to be able to do it, able to use it. There's not a whole lot of calc being done. I guess that derivative, but nothing like the past problems that we've had involving calculus. Okay, last one, part C. Inverse Laplace of 1 over s squared times s minus 1. So we can use this idea backwards now. This is the inverse Laplace of 1 over s squared times 1 over s minus 1. It's kind of weird to write that out. Okay. Now I could just split them because I know when I had it, the answer just went backwards. So this is actually the inverse Laplace of 1 over s squared is t, in convoluted with e to the positive t. Right, but they want us to work through that further. Right, we want to not just have a convolution, but maybe an expression for it. So I got 0 to t of, and we'll let the e take the second part. So I got tau e to the t minus tau. Reason I did that is that trick that we keep using, that now we have e to the t that can be pulled out. And then I'm going to have tau e to the negative tau d tau. Right, this is going to take some integration by parts. Not very much of it, but it's good practice. All right, so I got plus and minuses. I got d derivatives with tau and then integral d tau. All right, plus, minus, plus. I have tau, 1, 0, as far as I had to go. E to the negative tau, negative e to the negative tau, e to the negative tau. Okay, so we're going to get e to the t times, we're going to get negative tau e to the negative tau. And then it's going to be, that was this. And then now the second one is a minus e to the negative tau. And that's ran from 0 to t. All right. Once we plug this in, simplify, we'll be at our expression. So this is going to be negative t e to the negative t minus e to the negative t minus negative 0 times e to the 0 minus e to the 0. So this is e to the t. And we get negative t, e to the negative t, e to the minus e to the negative t, and then a plus 1. All right, I think there's a small mistake somewhere in my work, maybe. No, it just flipped around. Okay, so if I multiply this out, I get negative t, and then I'm going to get a minus 1, and then I'm going to get an e to the t. So that's an expression that we'd want because we could work backwards from that if I needed to. Okay, so that's convolution, and Laplace convolutions. The theorem is what we're really interested in this case for diffie-q, is because if I can get something to the convolution, then the Laplace transform is very easy because then we get to split that integral between its terms, which is very convenient.